Welcome to episode 129, Spotlight System Backup, where we focus on how backups prevent permanent loss and preserve organizational continuity. The CP-9 control recognizes that every information system will eventually face failure, whether through human error, corruption, or attack. What determines survival is not the absence of failure, but the ability to restore quickly and completely. Backups form the safety net beneath all other safeguards, capturing the state of systems and data so they can be rebuilt when primary copies are lost. A thoughtful backup strategy ensures that even catastrophic events do not erase institutional memory. It is both a technical and cultural commitment to resilience, proving that preparedness is measurable, repeatable, and verifiable. From there, backups are categorized into tiers based on impact and urgency. Not all systems require the same recovery speed or depth of protection. Tiering balances cost against business criticality. A payment processing database may need near-continuous replication, while archived research data can be restored over several days. Defining these tiers helps align resources where they matter most. For example, top-tier systems might use high-availability clusters and hourly backups, while lower tiers rely on nightly cycles. By mapping each system's role to its recovery requirements, organizations allocate bandwidth, storage, and attention proportionately. Tiering transforms backup from a uniform task into a risk-informed strategy. Building on that structure, defining cadences distinguishes between full, incremental, and synthetic incremental backups. A full backup captures everything at once, serving as a complete baseline but consuming time and storage. Incremental backups capture only the changes since the last backup, reducing load but increasing restore complexity. Synthetic incremental methods rebuild a full backup automatically from prior increments, providing both efficiency and simplicity. Choosing the right cadence depends on data volatility, recovery time objectives, and available infrastructure. For instance, a system that changes hourly might pair nightly fulls with frequent incrementals. Cadence design ensures balance, enough frequency to stay current without overwhelming resources. From there, encryption becomes the safeguard that keeps backup data private in both transit and storage. Sensitive information remains valuable even in archived form, so it must be protected as carefully as production data. Encrypting backups in transit prevents interception during transfer to off-site or cloud locations. Encryption at rest ensures that, even if media are lost or stolen, their contents remain unreadable without proper keys. For example, a misplaced external drive holding unencrypted backups could create the same breach impact as a live system compromise. By enforcing encryption automatically, organizations maintain confidentiality and compliance across every stage of the backup lifecycle. Extending that protection, immutability and offline copies defend against tampering and ransomware. Immutability means backups cannot be altered or deleted for a defined retention period. This prevents attackers, or even insiders, from encrypting or wiping historical data. Offline copies, often stored on separate networks or physical media, add another layer by removing the recovery source from potential attack paths. For instance, a ransomware outbreak that locks online systems cannot reach an offline tape or cold cloud archive. These air-gapped or write-once copies form the last line of defense. Together, immutability and isolation ensure that recovery remains possible even in worst-case scenarios. Building on the technical layers, snapshot coordination with application quiesce guarantees consistency across complex systems. A snapshot captures data at a single point in time, but if applications are mid-transaction, inconsistencies may appear. Quiescing, pausing write operations before taking the snapshot, ensures that databases, file systems, and services align properly. For example, freezing an e-commerce database just long enough to flush memory to disk creates a clean, restorable image. Coordination tools automate this sequence so backups capture usable, coherent states. Consistency at capture time prevents surprises at restore time, where even a few missing bytes could corrupt entire workloads. From there, maintaining detailed catalogs, indexes, and restore metadata ensures that what has been backed up can actually be found. Each backup operation should register not only the data it captures, but also when, where, and how it can be restored. Catalogs record job histories, indexes map file paths, and metadata links each backup to its configuration context. Without these elements, recovery teams face blind searches through vast storage sets, wasting precious time. A complete catalog acts like a map back to normalcy, letting teams target exactly which version to restore. Proper metadata management transforms backup storage from a black box into a navigable archive. Continuing on, key management must remain distinct from the backup environment itself. If encryption keys are stored inside the same system that holds encrypted backups, a compromise in one compromises both. Separation means using an independent key management service, hardware module, or secure vault that enforces strict access and rotation policies. For instance, a disaster recovery plan may store decryption credentials in a sealed physical safe or external digital escrow. Keeping queues apart reduces the blast radius of any single breach. It also supports compliance evidence that demonstrates clear segregation of duties between those who back up data and those who can decrypt it. Building further, test restores are the only true proof that backups work. A successful job log does not guarantee a usable recovery. Periodically selecting random samples or critical data sets for full restoration validates both integrity and process. These exercises reveal corrupted media, misconfigurations, and procedural gaps long before a real emergency. For example, a quarterly test might uncover that certain virtual machine images were backed up without dependent network settings, prompting a fix. Verifying through practice builds trust in the system and confidence among stakeholders. In backup operations, evidence of success is not the copy, it is the restoration. Extending reliability, tracking failures, retries, and coverage helps maintain consistent performance. Backup systems should generate alerts for missed runs, partial completions, or media errors, allowing operators to respond quickly. Trend analysis shows whether specific assets frequently fail or whether overall success rates are improving. Coverage reports confirm that all required systems remain included as new assets are added. For instance, onboarding a new application without updating backup policies leaves a gap invisible until recovery time. By maintaining visibility through metrics and dashboards, organizations ensure that protection keeps pace with operational change. In addition to monitoring, auditors and assessors look for concrete evidence such as job logs, configuration records, and retention proofs. These artifacts demonstrate that backups occur as scheduled, are verified for integrity, and adhere to defined retention periods. A complete evidence package might include a printout of recent job completions, a hash list proving file consistency, and documentation of secure offsite storage. Presenting these materials during assessments confirms that the backup control is both active and effective. Well-documented evidence transforms backup compliance from a promise into a traceable reality. From there, metrics such as backup success rates and time to restore help evaluate the overall quality of the program. Success rate reflects reliability. Time to restore measures readiness. A system that restores quickly from verified backups offers real resilience, not just paperwork assurance. Tracking these numbers over time highlights areas for improvement, such as slow media, bandwidth bottlenecks, or under-resourced teams. Leadership can then tie these insights to investment decisions, ensuring that recovery capabilities match business risk. Metrics translate backup performance into language executives understand, measurable assurance. In closing, reliable backups enable true resilience. The CP-9 control reminds us that every secure system must plan for loss, yet never accept it as final. When scope is clear, encryption strong, copies immutable, and restorations proven through testing, recovery becomes an expected step rather than a desperate scramble. Effective backups protect more than data. They preserve continuity, reputation, and trust. Through discipline and verification, they turn uncertainty into confidence and transform the worst day in operations into a recoverable one. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.